So there are many angles besides the common angles in the unit circle. The common angles cover really very few of the possible angles out there. We use them because they were based off of the 30, 60, 90 right triangle and the 45, 45, 90 right triangle, which we then eventually made the switch over to radians. But there are many other angles besides just 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians in the first quadrant, and all of their symmetric angles in the other quadrants. There are a lot of other angles in there, like, say, pi over 12, or 7 pi over 12. There are many other angles. So there's got to be a way to handle those without necessarily needing to go to a calculator. And as it turns out, there is. There are a number of different formulas in trigonometry, but the ones that we're going to study here are called the sum and difference formulas. Now, I actually find it a little bit silly to have a sum and difference formula, because they really are just two forms of the same. They really are just two forms of the same formula. It's just that one of them deals with subtraction. But we also know that subtraction can be written as addition of a negative. So with that in mind, we can do the sign, the sign of a sum or the sign of a difference with the same formula. So the idea is that if we can take some angle that is not one of our common angles, but if we can write it as a sum of two common angles, or again, any of their symmetric angles in any of the quadrants, then what we can do is take the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. There is a formula for the cosine of the sum of an angle as well. Again, if we can take any angle and write it as a sum of two common angles, we can evaluate it using cosine of the first times cosine of the second minus sine of the first times sine of the second. Those two formulas are somewhat similar, so they are a little easy to get confused, but remember, during your test, you're going to have access to these formulas, so not really a problem. We also have a sum and difference formula, or a sum formula rather, for tangent. So again, if we have an angle that can be written as a sum of two common angles, then what we can do is take the tangent of the first plus the tangent of the second over 1 minus the tangent of the first times the tangent of the second. Now, we're not going to go through the proofs of these formulas. They do exist. But at this level, I think to go through those proofs is probably just going to lead to more confusion than is necessary. So before we get into using these formulas, I'd like to talk about how to write a common angle as a sum or difference of other angles. So for example, let's take the angle theta is equal to pi over 12. The idea is that if we can write this as a sum or difference of any two of the common angles, then we will be able to use those common angles along with the sum formulas up above. Now, the common angles through the first quadrant are 0, of course, which isn't really going to help us if we're trying to write a sum. So the other common angles through the first quadrant are pi over 6, pi over 4, pi over 3, and then pi over 2. Now, part of what is going to make this tough is that each of these is a fraction of pi, but they all have a different denominator, and that makes it hard to figure out a sum or difference. But that's also part of the key. If we're trying to write pi over 12 as a sum or a difference, in order to add or subtract any two of these fractions, they need to have a common denominator. So it might help if we write each as a fraction with a denominator of 12. Pi over 6 can be written as 2 pi over 12. Pi over 4 can be written as 3 pi over 12. Pi over 3 is 4 pi over 12. And pi over 2 is 6 pi over 12. So as it turns out, there are a couple of different ways that we can write pi over 12. We can write pi over 12 as 3 pi over 12 minus 2 pi over 12. To put those back into our common angles, we can use pi over 4 minus pi over 6. Or, to fit the sum formula, pi over 4 plus negative pi over 6. Or, we can write it as 4 pi over 12 minus 3 pi over 12, which again, as our common angles, would be pi over 3 minus pi over 4, or pi over 3 plus negative pi over 4. So we have two different ways that we can write pi over 12 in terms of common angles. Now, admittedly, degrees are probably a lot easier to work with in terms of finding a sum or difference of two angles. So if the angle given is in degrees, like say 105 degrees, then it's actually pretty easy to find this as a sum or difference of the common angles. In degrees, the common angles through the first quadrant are 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So there's really only one good way to do this. We can write 105 degrees as a sum of 45 degrees plus 60 degrees. So it's actually maybe easier to do this with degrees, and that is an option too. We're still going to try to work with radians when we can, but it might be helpful to convert an angle given in radians into degrees in order to find two angles that add or subtract to it more easily, and then convert those back into radians. But that does add the extra work of converting and then converting back. So that being said, maybe it's not the greatest option. So let's see how these formulas work. We'll do one example with each. So suppose, and we'll use the angle we just had, suppose we want to evaluate the sine of pi over 12. As we said before, we have a couple of different ways to write pi over 12. I'm going to choose to use pi over 4 minus pi over 6. Therefore, sine of pi over 12 we can do by doing the sine of pi over 4 plus negative pi over 6. According to our formula then, this should be the sine of the first angle, pi over 4, times the cosine of the second angle, negative pi over 6, plus the cosine of the first angle, cosine of pi over 4, times the sine of the second angle, sine of negative pi over 6. And each of these is a sine or a cosine of a common angle from the unit circle. So the sine of pi over 4 is square root of 2 over 2. The cosine of negative pi over 6 is the square root of 3 over 2. Fortunately, the common angles all have x and y coordinates, sine and cosine values that have a denominator of 2. And that's going to make working with these a lot easier. We have the cosine of pi over 4, which is square root of 2 over 2. And we have the sine of negative pi over 6, which is negative 1/2. From there, it's just a matter of actually multiplying these things together. The square root of 2 times the square root of 3 would be the square root of 6. And in the denominator, we have 2 times 2 is 4. In the second multiplication, in the numerator, we have square root of 2 times negative 1, which is negative square root of 2. And that is over 4 as well. So since they are both over 4, we can easily combine them to get the square root of 6 minus the square root of 2 over 4. Not a pretty value. Well, let's face it though, none of the values that we get out of sines and cosines are typically pretty. I mean, occasionally we get something nice like a 1/2, but for the most part, they're all fractions that involve radicals, so hopefully should not be unusual that that's what we get here. But that's the best we can do. That is our answer. Let's try an example with cosine. We'll use a different angle this time. We're going to do a cosine of 7 pi over 12. So again, we need to find a way to write this as a sum or difference of two common angles. So I'm going to start with the angles again in the first quadrant, which is pi over 6, pi over 4, pi over 3, and pi over 2, which can be written as 2 pi over 12, 3 pi over 12, 4 pi over 12, and 6 pi over 12, respectively. And it should be pretty clear to see in this case that 7 pi over 12, then, is the sum of 3 pi over 12 and 4 pi over 12. So when we are doing cosine of 7 pi over 12, we can therefore do the cosine of 3 pi over 12 plus 4 pi over 12. And according to the formula for this, this would be the cosine of the first angle, 3 pi over 12, times the cosine of the second angle, 4 pi over 12, minus the sine of the first angle, 3 pi over 12, times the sine of the second angle, 4 pi over 12. Now, of course, I neglected to revert 3 pi over 12 and 4 pi over 12 to their original forms that are more recognizable, so I will do that now. 3 pi over 12 is really pi over 4. 4 pi over 12 is really pi over 3. Again, 3 pi over 12 is pi over 4, and 4 pi over 12 is pi over 3. Each of these is therefore a common angle, and therefore we can evaluate the sine and the cosine of each of them. So the cosine of pi over 4 is root 2 over 2. The cosine of pi over 3 is 1/2, minus the sine of pi over 4, which is root 2 over 2, times the sine of pi over 3, which is root 3 over 2. Now, hopefully it's not too surprising that we're going to get actually a lot of similar things here from what we saw in the previous problem. And the reason is that if we're using the common angles, there are only so many sine and cosine values that we're going to see. So it should not really be surprising that we actually see a lot of repetition in some of these. So we have the square root of 2 over 4 minus the square root of 6 over 4. And that gives us square root of 2 minus square root of 6 over 4. Let's try another example. This time we'll do tangent. Now what you're going to see a lot of in this is denominators of 12, because that is a common denominator for all of the common angles, so you will see that fairly often. Another example we might use here is, say, the tangent of 11 pi over 12. So again, we need to figure out how to write 11 pi over 12 as a sum or difference of common angles. As it turns out, we're going to need some that are perhaps a little bigger than what we see in the first quadrant alone. But again, as long as we can write it as a sum or difference of something that is among our common angles. 11 pi over 12 can be written as 2 pi over 12 plus 9 pi over 12, where 2 pi over 12 is pi over 6, and 9 pi over 12 is 3 pi over 4. So again, we might need to go something a little bit larger than what we just saw in the first quadrant. But again, as long as it can be written as something over 12, it certainly will simplify down, it should simplify down to one of our common angles. So therefore, the tangent of 11 pi over 12 is equal to the tangent of pi over 6 plus 3 pi over 4. Now, according to our formula, that should be the tangent of the first, pi over 6, plus, oh, that was fun, plus the tangent of our second angle, 3 pi over 4, over 1 minus the product of tangent of pi over 6 times tangent of 3 pi over 4. So a little bit different formula here, but perhaps not surprising that we're seeing it as a fraction like this, because tangent is the slope, which has a rise over run. And that would normally be in the form of a fraction. So perhaps not surprising that we see it that way. So tangent of pi over 6 is the square root of 3 over 3. tangent of 3 pi over 4 is negative 1. In the denominator, we have 1 minus the tangent of pi over 6 again, which is root 3 over 3, times the tangent of 3 pi over 4, which is, again, negative 1. So from here, it's just a matter of arithmetic. In order to add the fractions in the top, and again to add the fractions in the bottom, we will need common denominators. So in the top, we're going to write the negative 1 as negative 3 over 3. In the denominator, we're going to write the 1 as 3 over 3. And then, well, we don't really need to deal with, to write the negative 1 in the denominator as a fraction, because it really can just multiply the square root of 3 over 3 that's already there, which is being subtracted. So if we have a 1 minus negative square root of 3 over 3, we can just make it plus the square root of 3 over 3. So in the numerator, we're going to have the square root of 3 minus 3 over 3. And in the denominator, we're going to have 3 plus the square root of 3 over 3. This is a complex fraction, and we can simplify it, and the easiest way to do so here is to realize that since they have the same denominator in the top fraction and in the bottom fraction, those denominators can simply cancel out and leave us with the square root of 3 minus 3 in the top and 3 plus the square root of 3 in the bottom. And that is our answer there. So again, these formulas are not perfect. They are still somewhat limited, but they do expand our ability to do other angles. There are further formulas in trigonometry that will allow us to do yet more angles, as long as we can write them, again, as certain combinations of other angles. We will not be covering them here, but there are things called double angle formulas. There are formulas known as half angle formulas. And there are formulas known as product to sum formulas. All of these things can be used, and sum to product formulas. All of these things can be used to evaluate trigonometric functions of other angles that can be other combinations of our common angles. Now, it's, again, still not perfect, but if we want to get the exact values of certain other angles that are not our common angles, we can use these formulas to get exact values rather than decimal equivalents. We can always turn to a calculator to evaluate any of these, but we will always get a decimal equivalent of something that basically is an irrational number, so the decimal equivalent is going to be not the best form to use, but if we have no other choice, it is there.